Hey, Philip, how's it going?
Hey, pretty good. How are you?
Very good. So let's make sure screen sharing works. That's usually the difficult bit.
I think that should work. Let me see. Where is?
Yeah, a little button in the middle pointing up.
Where's the screen that I actually want to show?
Ah, okay.
There we go. There we go.
Oh, brilliant. So I see the editor view, and if you try sharing, what happens?
Let me see. Let me do reading view. That should work.
Yeah.
Can you all see that?
No, still, I think you're sharing a window and sharing the editor window.
Oh, that doesn't the reading view? That's odd.
Yeah, usually what happens is there's two separate OS windows, and you're sharing just one of them, which is
Yeah, no. That's let me. I guess I have to share my screen, my full screen. I usually don't do that.
That's the easy thing. This is a law interaction of Meet and PowerPoint. Yeah, now we can hear perfectly.
Okay.
All right, that'll work. If you can hide the little Meet sharing your screen thingy.
Okay.
Oh, no, that stopped sharing. There's a little button to the right that said hide.
Oh. Let me see. That's Oh, okay. Hide. There we go.
Yeah, okay. It's just a little bit less distracting.
Okay,
it's persistent.
Oh, there we go. Okay.
Perfect. All right, excellent. So let me start recording and give a really brief intro, and then it'll ding when it starts recording. 1 second. So hi, everybody. I'd love to introduce Philip Kim from University of Toronto, where he sits at the intersection of computational biology and bioinformatics and, like machine learning. Welcome, Philip.
Thank you. Should I get going? Just
please, yeah.
Okay, awesome. Okay. So yeah, thank you for the invitation to speak at the venue. I'm gonna talk a little bit about what we do in my lab, and I'll also touch a tiny bit about what we do in a company in a stealth company I co-founded, and I'll touch on both very briefly. Okay. So it's a very exciting time for protein science in general and for protein engineering, and especially when it comes to therapeutics. And I would argue that that what's driving this excitement right now is a process that's been going on for several decades, and this process has included the collection of a fair bit of data from biology. And it of course includes Moore's law. So we're having very powerful computers. It includes the development of novel machine learning methods to actually make use of both the data and the compute to get us to where we are. And so I've been doing this for a very long time, but I can tell you that there has never been as much excitement and as much sort of speed and progress as there is now. So it's really quite an amazing time to be alive and to be doing this kind of research. Okay, so I guess I can skip that because of the sophistication of the audience. So I'm going to mainly talk about de novo, the structure-based de novo design, and so I want to introduce a number of technologies that have been developed in the last just few years that really enable the de novo design of biologics of protein-based therapeutics. So we have one of the most important developments was the representation of 3D structure for deep learning models, and initially we had graphs, and this turned out to be an efficient representation for molecules, and now new approaches are these so-called SO3 equivariant approaches that are quickly superseding graphs. And my own lab has done some work on this, and we were among the first to introduce graphs to protein design back 3 or 4 years ago. Then the second was the development, of course, of transformers that everybody's very familiar with, and I'm gonna touch in the last section of my talk. I'm gonna touch a bit on work we did for using transformers for the design of zinc finger proteins. And then transfer learning has been very important for us because in many biological applications we tend to be in a low data regime, and we have to make use of transfer learning to get to better models. And then finally, of course, there's diffusion models, and that enable us to generate high quality samples. And my own lab also, we developed one of the first protein fusion models. But the development of technology is so fast right now that diffusion is already kind of outdated, right? And now there's newer, more powerful models that are coming online. And finally, of course, we have in the sequence space, everybody knows about language models, protein language models, antibody language models that are very powerful, and we've done a bit of work on this as well in my lab. Okay, and I just wanna note that that at our startup, we're sort of improving on the work that I did in my academic lab, and we're sort of supercharging this everything for antibody design. Okay, let me introduce to you very briefly how we go about protein design in terms of deep learning, and that's a bit of a stroll down memory lane. So back in the day, it was recognized maybe like 3 or 4 years ago that graphs are a good way to represent molecular structure. So the problem that we faced, or the field faced maybe 4 years ago or 5 years ago, was that how do we? So we have these powerful deep learning methods, but they've been rather mostly developed for images and for text, so for 2D or 1D type of data. And so how do we represent proteins or molecules with just 3D objects, right? And then the very early approaches were based on voxelization, right? So you simply make 3D pixels, right? And then you sort of try to fit your molecules into these voxels, and you do convolutions on them. And none of this stuff really worked super well. And so a big advance came when people started looking at graphs. And the main advantage of graphs here is these properties of rotation and translation invariance. So the main thing is, right, you have if you have a molecule in 3D space, right, and we describe its coordinates in 3D space in a global frame, and then when you rotate the molecule, or when you move the molecule, all the coordinates change, right, and so your model has to learn again that is the same protein. I mean, it's only turned, and that makes it pretty inefficient, and also you have to discretize your coordinate system somehow. So with graphs, you have to do neither. With graphs, the naturally rotation invariant, and then the naturally discretized, and then we can sort of come up fairly easily with a efficient representation of molecular structure that is efficient to learn on. And so these graph-based approaches are still pretty popular. So they're still sort of state-of-the-art or close state-of-the-art approaches that you make use of graph-based approaches. But increasingly, and I'll hint on that a tiny bit in a later part of the talk. Increasingly now there are superior approaches that are being developed, and these are largely these FC3 equivariant approaches that have some mathematical advantages over these graph-based approaches. So back in the early days, so that goes back to 2018 when we started the work, which feels like an eternity ago. We developed an inverse folding approach. So a protein design that solves the inverse folding problem. So you're given the protein structure, and you want to find the sequence that folds into it, right? And that's also known as the protein design problem. So what we effectively did is we represented the protein structure as a graph, and then we can train it on many structures, and we can train it on many sequences, and then the method can learn how to fill the structure correctly with a given sequence, and then lo and behold, our method called protein solver would then yield folded proteins. You can see here that when we measure the sequence identity, back to the benchmark proteins were shooting at around like 38-40%. And back then in 2019, 2020, that was state of the art, right? So by now new approaches have been developed that outperform protein solver with better engineering and better approaches. So but back then, so as I said, so we could prove that when we give protein solver a set of protein structures that are very different, it always manages to come up with a protein sequence that will fold into exactly the structure. And so this was back in the day, that was in the pre-AlphaFold world. So we had to use physics-based methods to actually fold these, but it still works. We can make use of other physics-based methods to convince ourselves that these really work. And this is based on molecular dynamics. So these proteins, when you simulate them on a computer, they don't fall apart, but they really stick together. And finally, we actually made some of these proteins in the lab, and we can show that they perform in biophysical experiments that they're nicely folded proteins, and that increase the likelihood quite a lot that they actually look like the way we designed them. And as I mentioned now, related approaches that outperform protein solver have been developed, and most famously protein MPNN, which came out last year, but which is really conceptually is very similar to protein solver. But it is admittedly a better engineered model. I just want to mention very briefly that these graph-based approaches like protein solver, protein MPNN, they operate on the local frame. And so molecular detail is much more difficult to capture, right? When we effectively we have to encode these distances here, or these relative positioning of different molecular features into several constraints, right? And when I operate in the global frame, I can much more easily locate these differences, and that's one of the sort of intuitive reasonings why with equivariant reasonings in a global frame are more efficient, and we at Fable we developed those modules for antibodies, and as we can see here in this sort of inverse folding sequence design problem. So the models we developed at Fable, and we call it REM, outperforms previous approaches. Protein solver is around here, and with graph-based approaches like protein MPN, where we go about here. And with protein MPN, with REM, we outperform the state of the art quite handily.
So what's the key idea? Because I get that you want global context, but are we talking about like a transformer or some other way of getting like globality?
Sorry?
How are you getting the global context? I didn't get the intuition.
Oh, okay. So it's simply that if you're it's when you talk about, so especially when you talk about a protein binding another protein, right? So what intuitively really matters, right, is that you get the small details right about what several amino acids interacting with each other, right? Mm-hmm. And that's much easier to do if you remain in a global frame. So if you know that these coordinates are close to each other globally. Mm-hmm. That makes it much easier for your model to figure that out. If you operate in the local frame, then you have one protein in a local frame, another protein in a local frame, and to figure out that these two atoms here are going to be close to each other, you have to go back to the residue frame, and then from the residue frame you have to figure out the direction, and then from the direction you have to figure out that actually you have to make several operations to figure out that these residues actually close to each other. And that's sort of intuition.
So, but now we're getting, so the context is we have a graph. So let me get you in the graph convolution. So my intuition here is I have a sequence, which is a graph, and I have the what's called the amino acid direct bonds. They're not 3D bonds. And then you have a bunch of graph edges that you just don't know the distances along the graph edges. And from your library that you train on, you infer what the distances might be. And then, actually, tell me if I get this right. Once it folds, do you get additional bonds, or are these the sequence all the chemical bonds?
So we have to distinguish here between covalent bonds, so between sort of bonds between the atoms and the molecules, right? Mm-hmm. And non-covalent interactions between different molecules, right?
Right.
And so what is sort of easier for the model to figure out when you operate in a global frame is the relative positionings of atoms between two different molecules. All right.
What do you mean by that?
Sorry?
You mean which atoms on different molecular arms, which are in 3D space close, or
Yes.
in sequence space?
Yes. So you're talking about two different molecules, right? And you wanna so in the antibody antigen problem, right? So you have or in the protein interaction problem, right? So you want to make a protein that binds the other protein as well as possible, right? And for that, what you have to get right is you have to get the molecular detail right at the interface, right? And for that, it's gonna be really important, what sort of the molecular detail of like single atoms or single residues is going to be really important on their relative positioning, right? And so that's going to be much easier if you have some view on that in the global frame, because in the global frame you can easily tell whether things are close to each other or not.
Okay, and then yes, and how did you incorporate this global frame? Because it seems like, hey, once you get this graph, you get some idea of kind of how the different arms of the protein.
Oh yeah. Okay. So I'll sort of have to refer you to the literature on that. So it's going to be a little math to go through, but ultimately sort of the idea is that you can make this model staying in the global frame, operating with coordinates, right? But what you have to do is you have to find architectures that are equivariant, so that operate so that they can remain operating in the global frame. So the invariance of graphs is sort of a simpler way out, right? But it's ultimately a bit less efficient.
But it ultimately what?
It's ultimately less efficient. For the model to work. Okay. Right. So secondly, I'm sticking with the graph with the graph approach for a second, because we're still talking about what's somewhat older work here. So what we wanted to build was a predictor of peptide binding, which is related to protein binding, and so what we're trying to do is we were trying to build a novel attention module that could operate in both directions, and we've developed this module called reciprocal attention that enforces symmetry. And what that effectively allows us to do is to let the peptide talk to the protein, and the protein talk to the peptide in both directions. And sort of chemically or biochemically, what that corresponds to is to allow for conformational changes on both sides. And then we obtain a model that can model that can predict the binding side of peptide quite accurately. What we had to do for this model to work is we had to incorporate transfer learning, and that's something that you see quite often in biology, is that the actual training data is relatively small. And so for peptide protein binding, if you look at the PDB, which is essentially the study of data there is on a structural level, you end up with about 3,000 complexes. So that's not a huge amount of data. So what you then have to do is you have to be a little bit smarter about it. And so what we then do is we generate a much larger pre-training data set that is related to our problem, but is not quite like it. And for the peptide protein problem, we generate this fragments data set. So we have a way to effectively identify fragments of proteins that are binding other proteins, and these are by definition peptides, but we're extracting them from protein complexes. And so we're extracting them in such a way that they're quite likely to bind by themselves, but it's not totally clear that they will. So it's a lower quality data set, but they have many properties that many properties that the peptide protein complex would have. And this data set is much larger, so we have about 500,000 of these fragment complexes. And so we use this to pre-train our model, and then we fine-tune on the real data, and we get a final model. And we can see that that our performance is substantially larger when we use the pre-trained set, and it's somewhat lower if we use only a peptide complex, so if we don't have fragment complexes. And you can see here in this one example that our pre-training really helps. And likewise, when we use a sequence-based model, we do substantially better if we use the pre-trained thing on known embeddings. Okay, so finally, I want to talk about de novo protein design. And de novo protein design is quite a difficult problem. So I spoke very briefly about inverse folding. So when you have a protein structure in mind, you can use an inverse folding algorithm like protein solver, protein MNN, to get the sequence that will likely represent this protein. When you do de novo protein design, you want to generate both the sequence and the structure of a fully novel protein that will form a real protein. And these proteins may never have been seen in nature, right? So they're fully novel. You can do this either unconditionally to get fully novel proteins, or you can do it conditionally. You can condition on some sort of scaffold or motif, some sort of target to get other proteins that are conditioned somehow on a motif. And for this, we developed protein SGM. So diffusion is not really that old, but it only became popular like 2 years ago when I started winning the image generation competitions. So before, and it was all GANs, right? And about 2 to 3 years ago, the diffusion models, the DDPMs, SGMs, and all the model following started to win. And DALI or stable diffusions are examples, and I think I can sort of skip that now, so you're learning the noise, right? And so we developed a protein SGM based on the SGM framework, and so this framework allows us to effectively use an image-like representation of proteins. So we're representing a protein with these 4 matrices plus a padding matrix that effectively just uses images. And so one of the matrices is effectively just a graph of the distances. So a weighted graph of distances of the C beta to C beta atoms in each residue. And then the other matrices are angles that describe different features, molecular features of the backbones. And so together, these so-called 6D representation gives us a full representation of the backbone. And then we can use a relatively off-the-shelf diffusion model to essentially learn how these 6D coordinates look like for real proteins, and then we can generate new ones, and then use a sequence design method like protein solver or MPNN or that to get a full atom structure of both the sequence and the structure. And I can sort of proudly announce that protein SGM was one of the first protein diffusion models out in our archive and last summer, and that also feels like an eternity ago. And we were out essentially earlier than Chroma or Baker-Saraf diffusion. So I should say Arc diffusion is Chroma and Arc diffusion are both quite good models, and at least Arc diffusion does outperform protein SGM in some metrics. Okay, so what we could easily show is that we're getting out proteins that by any sort of computational metric, like by Rosetta energy, like by biophysical energy, we're getting out things that look just like real proteins. And if you look at them here, they look just like real proteins. And by the sort of TM score metric, so the TM score less than 0.5 to the PDB means that they're new proteins, that they're considerably different from anything that's in the PDB. So these are proteins that have really never been seen before in nature. And this SPTM score is a self-consistency metric. So basically, in this AlphaFold world, we can sort of trust AlphaFold that it's gonna do a good work, it's gonna do a good job, and this Omega Fold is gonna do a good job, given a sequence of getting the right structure. With SCTM, we essentially measure if we're starting, we're getting a protein designed by Protein SGM, we're then have a structure, and then we're designing the sequence, and we're getting a full atom model. And then we're taking the sequence out and we're refolding it again with Omega Fold or AlphaFold. Do we get the same structure back? And here we're on our average SCT, or we're getting a large number with SCTM scores of 0.8 and 0.9, meaning that they're effectively the same structure. So that's actually a quite a high performance of in terms of designability of our structures. And then finally,
a question about kind of the application domain. So when you say it's a backbone, are you saying that you can? Is it just the backbone of a protein to give you an overall 3D design, and you can attach like binding sites to that structure, or is it the fully finished kind of protein that you have to design every time?
Just maybe a slight nuance here is that when we talk about backbone, we're effectively talking about just sort of the core, the core of the protein without side chains. So in the protein world, we're distinguishing between the backbone, which is sort of the peptide string of the protein, and all the side chains, right? And so protein SGM, like Chroma, like RFDiff, is ultimately a backbone model. So it'll generate this sort of representation, which is basically just sort of the naked backbone. So just sort of the polyglycine, if you will, sort of something. So just peptides fused together without any side chains. And then to make a full protein, you have to use a sequence design model to put in all the side chains, so that it'll actually fold into that structure that you want it. So that's just that's a nomenclature we usually use in the protein world.
Okay, thank you.
So, but what you have to do, of course, is you have to show that that the proteins you're making are real, and we took two examples here that are fully novel. So these don't exist in nature, these proteins, right? And again, we're making them in the lab, and we can see here. So in this experiment, this shows that this protein is clearly a helical protein. That's by this experiment called the CD spectroscopy. And so this protein is also clearly a helical protein, and this experiment shows that it has what people call a nice two-state folding transition. So it means that it's a real protein that behaves like a normal protein, and then in all likelihood it looks like this because AlphaFold lets it looks like this. So we're really making real novel proteins never seen before in nature. And maybe to touch on what you asked earlier, is what we can also do is we can use inpainting. So we can fix certain regions of the protein, and we can only noise other regions, and then do inpainting. And we can do that here by fixing the scaffold here, and then just inpainting this part of the protein. Or we can also just fix one motif of the protein and then inpaint the whole scaffold, and we're getting sort of other proteins that have this region the same, but then have different scaffolds. And in each case, it generates protein SGM will generate real folded proteins and inpaint both domains and scaffolds.
Question, actually. By the time you started painting, the natural question becomes designer proteins where, depending on where you bind other proteins, it starts changing shapes, like the walking molecules and whatnot. Yeah. How feasible is that with this foundation?
Oh, so it is quite feasible. So we definitely do that, and I'll get to that actually in a couple of slides.
Great, thank you. So
so just as a small segue from that, but we'll get back to full protein later. We also we've been working on peptide therapeutics and peptides in general for a long time, and so we also developed Helix GAN like a long time ago, and Helix Diff as full atom peptide generation models that are again, so Helix GAN was again, and then Diff is an SGM. That builds peptides built based on hotspot residues, and we can actually show that GLP-1 So GLP-1 is now become a household name. So everybody knows Ozempic and Rybelsus and so you may have heard of the weight loss drugs, right? These weight loss drugs that you inject yourself, that you inject into your stomach. And so GLP-1 is one of the most famous peptide drugs because it's the most popular one. And so what we can do actually, we can generate new versions of GLP-1 that are composed of these so-called mirror image amino acids, so D amino acids that are the mirror image of normal amino acids. So you may have heard of chirality. And anyways, that has a number of that has a number of advantages from a drug development point of view because they're very stable, so they don't degrade in the bloodstream. So GLP-1, has a limited half-life in the bloodstream. If you can make them as mirror images, they'll stick around much longer. So exponentially longer than GLP-1. So you would have to inject yourself much less often. We can show here that we can make quite easily. We can make these mirror image versions of GLP-1 that work a little bit worse, but are still active in activating the GLP-1 receptor. So would actually be at least viable alternatives to these therapeutics. Okay, that's just a little segue. So I wanted to talk very briefly then now about using an SGM type approach to make antibodies. And antibodies, of course, are molecules that bind other molecules that can be and are very popular therapeutics. And so so here we simply developed an SGM type method to form antibody design, and we can use that to design especially the H3 loop, so that the most important part for antibody binding by inpainting. You can see here by these metrics, by the amino acid recovery rate or by the RMSD, by the similarity to the known benchmark, we outperform sort of the from previous methods like diff-AB by we sort of edge it out, and you can see here these are sort of a real antibody loop that's been generated with antibody SGM, and we're putting that up on archive pretty soon. I just want to mention that at Fable we developed our own diffusion model, and here we're outperforming the state from previous work by quite handily, both by AAR, so by the recovery rate, and by RMSD, by similarity to known loops, and we're getting realistic antibody candidates out of our diffusion model. And let me just skip that. So okay, so I wanna now talk about the dynamics of the how do we incorporate dynamics into our machine learning models, and that's really sort of the next step, or then the next frontier in machine learning for protein structure. And so this is particularly important for peptides. It's also important for antibodies with CDRH3 loops, but these are highly dynamic molecules, and also for peptide macrocycles, which are important to the drug class. So AlphaFold and the other folds effectively have mostly solved the single structure problem, right? But what remains to be solved is how do we incorporate dynamics? How can we capture that the peptides really, or proteins really are dynamic molecules? And so what we need is methods that can learn the conformational space. So so there are sort of physics-based methods to do that. And as a physicist, you think of conformational space as the energy landscape, right? And then there's minima and maxima, right? And here's a couple of minima, and it makes it in this minimum, and then go to other minima, sorry. And so the main approach, the main problem is that we even if you have a good function of the energy, and these are usually described as force fields, then it becomes computationally very expensive to describe the entire landscape. And so especially if you have a trajectory-based approach like dynamics or Monte Carlo, it's still prohibitively expensive to sample the entire landscape, even for our best supercomputers that we have in the world. So, and just to give you an idea, so with sort of modern, with modern GPUs, we can get to like hundreds of nanoseconds. But getting tenths of microseconds, even that is going to be quite expensive, for even just for one molecule. And if you want to observe the formation of a beta hairpin of a peptide, that put it at the edges for a single peptide, that put it at the edges of what a modern supercomputer can do. Okay, so we can solve this with machine learning. So what we can do effectively is we can train a machine learning method, the so-called boltzmann-generator, to effectively learn the transformation from a Bayes distribution, like in this case, a Gaussian, to a proposal distribution that operates in the peptide atomic coordinates. And this distribution here, we want it to be this energy landscape, right? And then if we can train such a Boltzmann generator, we can train our method to effectively learn the entire energy landscape of the peptide in one go, and we can then effectively describe the conformational or the entire conformational landscape of the peptide using this approach. We built one of these, and initially we built it on CNFs, and later so we started this work before really diffusion was a thing, and so we initially used CNF methods because we need network invariability, and then later on CNFs are quite tricky to deal with. So later on we changed towards diffusion models, and now of course there's the new shiny thing, and the new shiny tool in the box is flow matching, and so I think the next version of PepFlow is going to be a flow matching model.
So question.
And sorry?
I mean, this sounds like a Gaussian kind of approach where you have this is where I get lost, because now I'm not familiar with Boltzmann generators, but it sounded like, like a Gaussian kind of a process, except this for the molecular bits, which is like, what's the intuition there?
Sorry, I mean, so the Bayes distribution, it can be, it doesn't have to be Gaussian. We use a Gaussian here, and then in diffusion mode, it has to be Gaussian, right? But so the intuition is just that we want to learn this Boltzmann distribution of the molecule, right? And importantly, we want to learn that in a sequence dependent fashion, right? So we want to learn it. We want to basically, once you give us a peptide sequence, or just sort of a general descriptor of the chemical properties of a peptide, then we want to be able to simply get the Boltzmann distribution out in one go, right? So that's the goal, and we can do that by training by doing training in two phases. So training on known data, we call training by example, and then the key is if you have such a Boltzmann generator that's invertible, you can train by energy. You can actually use this energy function here to then flow back and to then train your Boltzmann generator on generated conformations.
So then what makes it, I mean, I guess I can imagine just like a Gaussian process, just like whenever I get a point, like dump a Gaussian there and approximate that way. But it sounds like this sequence sensitivity gives you something more.
So you can of course do that. So given the inner function, you can always sample, right?
Yeah, exactly.
You can always sample, but it's just very expensive, right? So in sort of the classical sort of physical chemistry world, we have been doing this kind of sampling for decades, pretty much, right? With molecular dynamics or MCMC, but it's the main problem is it is really expensive, right? And so and especially if you want to do design, right, then you want to sample not one, not tens, not hundreds, not thousands. You want to do sampling on millions of possibilities, right? And so that's still astronomically expensive. So you simply can't do that. So that's why. So what we want to do is we want to build something that given the peptide sequence, which is a molecular descriptor of a molecule, we want to get out the conformation, the entire energy conformation, the entire conformational energy distribution for free, or not for free, but for much cheaper.
Oh, so should I be thinking of this as a generator model that generates the entire space, the entire distribution?
Yes, effectively.
That helps the intuition a lot. Thank you.
Effectively. So in PepFlow, right? So PepFlow is a three-stage model. It first has, so importantly, it contains a hypernetwork. The hypernetwork effectively predicts the parameters of the other networks. So in this case, we have a backbone network, and we have a Rodeman network that's just the side chain. And for very technical reasons that we don't have to worry about, well, we also have a coordination network. You can see here that this backbone network learns sort of how protein backbone is supposed to look like, and the Rodemer network learns how the side chains supposed to look like, and then finally this coordination network would learn that for the hydrogens. But a key part of it is that we have this hypernetwork, and that makes it fully sequence dependent. So we can just drop in a new peptide sequence into PepFlow, and it'll generate automatically the allowable conformations for us. So what we can see here is if we can generate peptide conformations from PepFlow, and we almost always get realistic looking peptides. And you can see here that instead of the normal molecular features like bond lengths or bond angles or these Ramachandran plots, we're effectively getting things out that look just like a round truth. So it learned basically most of the molecular physics that we as a field know about. And so that holds true also for these bond angles here. And you can see here that for this particular chi3 bond angle, so the ground truth appears in blue and the generated ones are in orange. So it allows this deviation here. But I would point out that this is a feature, not a bug, because for PepFlow, because the oxygen, this is a carboxy group, right? And chemically it's indistinguishable whether it's flipped this way or it's flipped this way. And because in our case we distinguish these atoms, so we allow both conformations. But that's really just a representation of the chemical reality. And then you can see here that we're very well representing the molecular dynamic simulations. And when we use PepFlow in a structure prediction kind of way, so you can actually do that. You can actually just get it to predict the best structure it thinks exists. We do edge out the state of the art. So we're slightly edging out AlphaFold and ESM-fold, and there's a number of structures where we do substantially better. Most importantly, when we compare ourselves to the conformational ground truth, which is NMR ensembles, so we're actually doing we're actually doing quite well at covering this NMR example. So we cover about half of the conformations in the NMR examples, and so this gives us a pretty good coverage of what a peptide looks like really in reality. And then finally, for application purposes, we can use PepFlow to generate macrocycles, and this is important as therapeutics. And when we look at it here, so we can actually use PepFlow to quite accurately predict the structure of macrocyclic compounds, and we can use PepFlow in a generative way to generate binding peptides condition on the pocket. And what we can then use, and what I think is very exciting, is to do generative on a macrocycles condition on both binding pockets and set permeability, which is sort of a holy grail in macrocycle structure prediction and macrocycle development. Okay, so and just to close on the PepFlow part, so the development of technology in this area is extremely fast. So as I said, when we got started, we developed PepFlow as a CNF. And that did work, but it was really difficult to train because the CNFs tend to be very expensive to train because you have to solve an ODE for every time you want to train the data point. Then current PepFlow is based on score matching, right? And it uses a hypernetwork, and that works quite well. So we're right now Osamo is very busy right now bringing online PepFlow++, which is built upon a PFGM++ architecture and that in our hands actually does lead to quite a considerable performance increase over SGMs, and we also replace the EGN layers with equiformer layers, so which gives us a bit more it's a bit of a more expressive version of these equivariant neural networks, and then we'll be enabling straight binary design. Okay, my last story I want to tell is about in vivo gene editing, and so there's an AI aspect here too. But I just want to mention real quickly when we want to do when we want to do therapeutics. So what I've talked about so far is mostly targeting the protein. We can also target the mRNA with using these newer or these sort of other approaches. But what we want to do is we want to target the gene directly, and we call this epigenetic editing. And what we want for that is we want to use a transcription factor that we reprogram, and then we can alter the gene expression of any gene we want to, and we can use that for a variety of therapeutic purposes. So there are a number of technologies out there, and many of you may have heard of CRISPR, and there's also TALENT or other technologies. So all of these are great technologies, but all of these have a problem, and the main problem is that they all come from bacterial proteins, and it's generally not a good idea to inject ourselves with bacterial proteins, because our immune system will not like it and will react quite violently. And so that's a known and very big problem with all these methods. If you want to make drugs or therapeutics that are administered in vivo, so that we want to inject ourselves with. It works great for so-called ex vivo applications. So you take out part of your cells, you edit them in a lab, and then you put them back in, and that works great for like sickle cell anemia, for other applications. But for the majority of applications where you want to do in vivo, this is a big problem. So the path we went with zinc fingers, and these have the big problem: A, they're smaller, so they're easy to fit and deliver, and B, they're fully human, so they're much less likely to be immunogenic. So the main problem is that the zinc finger problem has never been solved. So zinc fingers have been fiendishly complicated. So they bind DNA sort of like this. So this is the representation of DNA, and they bind like this. But it has been very difficult because they bind in these long arrays, and these arrays, all these neighbors, all influence each other, and depending on how this one looks like, this one will have to differ, and depending on this one looks like, this one has to differ. So you have sort of a combinatorial explosion of problems of solutions, and so this code of how to make a zinc finger that will bind a given piece of DNA has never been solved, and it's not for lack of trying. So there's been 3 decades of work going into this, and as I said, there's this adjacency problem here, and so my collaborator had an animation made. So basically, these adjacent fingers have to be compatible, right? So you can have these fingers, and so this one doesn't fit, this one doesn't fit. But you have to find a compatible pair, and once you have the pair that fits, then everything is good. But you have to make many of these pairs. So at least 6 fingers consisting of five adjacent pairs to get them to fit. So that has been a large problem. So so what we did is we took an approach of doing a fair amount of experiments to get which helices are compatible. So we solved for the single helices, and then we solved for the 2 helices that are compatible, and then we built a language model. And this language model is a so-called hierarchical language model. So we have here these classical transformer architectures, right? And the DNA binding problem is a classical transformer problem in the sense that we're putting in DNA sequence, so with 4 bases, and we want to get out amino acid sequences, so 20 residues, and so it's effectively a translation problem, and so you can build a transformer each to solve the single helix problem, And then on top of that, as the hierarchical model, we're putting in another module that solves the compatibility problem. And we have enough training data to train both the lower level modules and the upper level module. And lo and behold, this model works very well and works by far and away better, as you can see in these comparison plots, than any model that existed before. And when we test this model to design new zinc fingers, we get that almost all of them work, and a quarter of them works really well, which brings us about level with how well CRISPR works, right? So in terms of accuracy, so we're about as good in making new zinc fingers to target a certain piece of DNA as you would when you get to what CRISPR guide RNAs, and then we can use that to reprogram transcription factors. So we can effectively take a natural zinc finger transcription factors. We can cut out the zinc fingers, and we leave its effector domain. So what actually will influence the DNA to regulate up or down. We can put in a new set of zinc fingers, and then now we can regulate the expression of any gene in the genome at will. And so we can actually, let me skip that. So what we can easily do, right, is we can take an activator, we can test it here in this test reporter system, and we can see here we get a very nice activation. We can also use the repressor system, and we get very nice repression of this gene here in this reporter system. What we've already done is we've used this to activate or repress certain disease genes, and in this case here, we can repress alpha-synuclein, and that's a gene that's been associated with Parkinson's disease. And we can find a number of zinc fingers that are very efficient in repressing alpha-synuclein, making them potentially valuable for treating Parkinson's disease. Or we can make zinc fingers this activated protein CDKN1, which would also be therapeutically relevant. Finally, our initial designs have many off targets, and the volcano plots here you can see here. These are the intended targets. You can see here this is how much they were activated, and this is how significant it is. So you can see here we do repress the target and we do activate the target quite well. But we can see here there's a spread of other stuff that happens, and we don't really want that, right? We only want our target to be activated in this case. So we can do some engineering, and with some engineering we get better zinc fingers that in this case sort of is almost as pristine specificity, where we only upregulate our own target, but nothing else. Okay. So I think that's it. This is my lab, this is my funding, and I also want to acknowledge the folks at Fable Therapeutics, and I'll thank you for your attention.
Well, great. Thank you very much. Ashia, are there any questions on the call? Well, then I guess maybe a big picture question is, to what extent is experimental data a limiting bottleneck? Because that seems to be the most expensive bit of the entire flow you've been describing so far.
Well, I mean, so especially in the structural world, right? So getting new protein structures, especially protein complex structures, is still quite an undertaking, right? So it's still pretty expensive to get that. And when you talk about when we talk about the antibody antigen problem, right? We would certainly be doing much better if we had 10 times the data or 100 times the data, right? We probably won't be getting 10 times the data anytime soon, right? So my personal belief is that with and I put my money where my mouth is, right? So we're doing that. We're doing that at Fable. Is that with sort of smarter use of the existing data, we're going to be doing much better, right? And so I think the more modern models do get you stuff in this field, and so just the adoption of so we're in a situation where we we can simply adapt the sensible events that come to us, are given to us from sort of the broader machine learning field, and the ones that really pay dividends do pay dividends massively. And that's a good example was diffusion, right? I mean, diffusion, just a few years ago was sort of a kind of an obscure machine learning concept, and now it's been transforming, certainly the protein world, but also many other applications, right?
That makes sense. And okay, so I noticed some of the things you were doing, like leverage physical models, where you just had some foundational data sets that the protein folding is maybe AlphaFold was based on those, but I didn't hear much about like any hybrid methods that said here are physical constraints like conservation of momentum or whatnot that guided your ML approach. Like, would those constraints be useful, or would partial physical models be,
Yeah, so I'm still of the opinion that sort of this physics-based stuff is still useful. I should probably concede that that their usefulness, both perceived and real, has certainly gone down in the last couple of years, right? So it's been increasingly recognized, and it's been increasingly proven that that these fully data-driven methods have outperformed physics-based methods, at many more things than we would have thought. I still think that there's still something there for physics-based methods, but I think the jury is to a certain extent out. To what extent we will still be using physics-based method in, let's say, 5 years from now. I mean, so I would have 5 years ago I would have thought that most things around at least protein design, or sort of protein binary design, we would still be doing like force fields and these sort of things, right? And it turns out we're at this point we're using very little of that at this point. I mean, there's still a tiny bit of it in there, but it's not much anymore. I would say that for where there does seem to be still a sense for at least physics inspiration are these these new generative models, right? These new generation generative models, like PFGMs have physics inspiration, right? Flow matching has a physical inspiration, right? So there is still physics has still some stuff to teach us, I think in that sense.
Right. So because you're pushing it in that, because there's a bunch of, there's a whole literature at this point on having, I guess, physics models with a bunch of bits missing and learned by ML to make the whole thing faster. From just making a neural surrogate, and there's many ways. So I guess the real question here is, let's see if my interpretation is reasonable. ML-based models say, well, the space of possible behavior is not so big. Here it is, approximately. Physics-based models say the space of possibilities is enormous, and with a lot of work, figure out which subspace is this particular thing. And to what extent can we get physics models to just focus on the tiny space that is actually feasible and be, a million times faster?
Yeah, okay, so that's of course. So there's I think there are several ways this union can help, and that's certainly one way, right? I think the other way is, and there's sort of a whole literature on that, is to effectively still make a physics-based processes, right? So for instance, there's this whole field of generating learned force fields, and do MD molecular dynamics with learned force fields, right? Because the rationale for that is that that's something I've that always made sense to me, that sort of an amber force field or a charm force field, right? It was always data-based in the sense. It was never real physics, right? Because real physics is quantum mechanics, right? And you can't, and then you have to do DFT, or you have to do something to get to quantum mechanics, right? So you always had some sort of data-driven thing. And why not make it more data-driven, right? Why not replace your 10 parameters with a million parameters and learn them something, right? And so I think that's now a growing field, and I only follow it like a bit in my peripheral vision, but there seems to be some quite promising work in that realm.
Yeah, that makes sense. Multi-scale physics is exactly this. You ignore the lower levels of structure, but nobody uses, well, it's still emerging how to use ML as some of these lower level, more detailed physics, within high level models.
But I think that's an exciting field. But I think there's a lot of work on going right now.
Okay. Well, sounds good. Well, yeah, thank you very much. It was fascinating.
No worries. Thank you guys for listening.
Great. Thank you. Have a good rest of your day.
Bye.